question. Section 14.4, linear plane, tangent planes and linear approximations. So in this section, we're going to try to describe what it means to be differentiable for a function of more than one variable to, or several functions of more than one variable. Sorry. Sorry. Okay, sorry about that. But before I can do that, I need to give you some terminology so that you can do some of the computations that we'll be asking you to do. So this first part will be just a whole bunch of definitions and, well, a few theorems. So let me start. Recall, the derivative from Calc 1 is just the best linear approximation to a function at a point. This is actually going to be our definition, our idea, our motivating idea that will give us the definition of the derivative for several functions of several variables. Okay, so first I need to tell you about, well, since I'm saying it's the best linear approximation, well, I have to tell you, what does it mean to be linear? And so let me give you the idea, the definition of a linear transformation. So let V and W be vector spaces over a field F. And let L be a function from the vector space V to the vector space W, such that if R is in the scalar field and if S is in the scalar field, and if U is a vector in the vector space V and V is a vector in the vector space W, no, V, then we have that L at RU plus SV is just R times LU plus S times LV. And so if this occurs for every RS in the scalar field, every vector UV, then L is called a linear transformation from the vector space V to the vector space W. Some notation, HOM. So HOM from the vector space V to the vector space W. So HOM VW is just a set of all linear transformations L from V to W. And so rather than, a lot of times we'll say let L be a linear transformation from V to W, we'll just say let L be a member of this set. So it'll be a shorthand notation. Sometimes I'll use it, sometimes I won't. So let's recall the definition of a field. So let F be a set with the following properties. First, it has to be closed under addition, meaning we have defined some operation on this set such that if you add two members of this field, you still get that they're a member of the field. And so the closure property for addition says that there is this operator, we'll call it a plus, from the Cartesian product of F cross itself to F. And so we have that there exists some binary operation. the closure property for multiplication says that there exists some operator, and of course, well, this is called a binary operation since it involves, well, the Cartesian product of two things. The closure property for multiplication says there exists some operator from the Cartesian product of the field F cross it to the field F. And so it just takes, and of course we use, rather than the notation, the regular notation where it's plus A comma B, you know, we're evaluating an A comma B, we use the infix notation. So we would say A plus B. And similarly, we'll write A times B. The commutative property for addition. If A and B are members of the field, then A plus B is equal to B plus A. Here, of course, we're using this infix notation, where we'll always use that. The commutative property for multiplication says that if A and B are members of your field, then A times B is the associative property for addition, which says that if A, B, and C are members of your field, then A plus the sum of B and C is the same as the sum of A and B added to C. The associative property for multiplication, which says that if A, B, and C are members of your field, then the product of A times B times C is equal to A times the product of B and C. The existence of an additive identity, sometimes called an additive unit, is, well, really it's a nullary operator, meaning that it takes nothing, the empty set, and so this operator goes from the empty set to the field F, and this field F has some element, zero, which we'll denote by 0. So there exists some element 0, and it has certain properties, such that if A is a member of your field, then A plus 0 is equal to A. And so A plus the additive identity is just the original number, A. So this means that this is a right additive identity, but by commutativity for addition, we have that it's also left additive identity. So we just say it's an additive identity. We have the existence of a multiplicative identity, the multiplicative unit. Again, this is a nullary operator. It goes from the empty set, so this operator goes from the empty set to the field, well, without the additive identity. The reason for that is that we want that this field, we don't want 0 to equal 1. Okay, so that it has more than one object in your field. Okay, so there exists an element 1 in the field, not equal to 0, such that for every element A in your field, A times the multiplicative identity is just equal to A. And so that means that this quantity A is a right multiplicative identity. And similarly, 1 times A is equal to A by the multiplicative property, the commutative property of multiplication. The existence of additive inverse. So this will be a unary operator. It will go, the inverse will go from the field into itself. And so for every member of your field, A, there exists another member of your field, denoted by minus A, such that A plus the additive inverse of A is the additive identity. And so this is a right additive inverse by the fact that addition is commutative. We have that the additive inverse of A plus A is just the additive identity. The existence of a multiplicative inverse. Again, this will be a unary operator. You'll take all non-zero elements of your field to a member, a non-zero member of your field. And so, if A is a non-zero member of your field, then there exists another element of your another non-zero element of your field, denoted by 1 over A, the reciprocal of A, and it has the following properties. A times the multiplicative inverse is the multiplicative identity. And so that means that this reciprocal here is a right multiplicative inverse. Since multiplication is commutative, I have that the multiplicative inverse of A times A is just a multiplicative identity. So it's both a right and a left multiplicative inverse. Lastly, I have that multiplication distributes over addition. If I have elements A, B, and C of my field, then A times the sum of B and C is the sum of the products A times B and the product A times C. Okay, so let's recall what a vector space is over a field. So when we did this back in chapter 12, I gave you the definition, but it was more or less the properties of a vector in R2 or R3. So now I'll sort of state it where it's more explicit, where I say that, this is for any set following that has these properties. We'll call this a vector space over some field F. So let's do that. The vector space V over F is defined as follows. So let V be a set and let F be a field. Then, if there are these binary operations of addition and multiplication, and they'll be different than what we did up here, because this is a scalar field, and they had the following properties. First, the closure property for vector addition. So there exists some binary operator, denoted by plus, that goes from the Cartesian product of V into itself, V. And it satisfies the following properties. The commutative property for vector addition. If U and V are vectors, then U plus V is equal to V plus U. If U and V are in the set V. The associative property for vector addition. If U, V, and W are in the set V, then U plus the sum of V and W is the same as the sum of U and V added to W. So these are very similar to what we had above, but now it's for vectors. The existence of a vector additive identity. Again, this will be a null area operator from the empty set to the set V. There exists some member of V, and we'll denote it by 0, such that for every member u of v. U plus the additive identity is u. And so this is a right, this number here, or this vector here, is a right multiplicative, a right additive identity. Similarly, using the fact that addition is commutative, we have that this is also a left additive identity. So the additive identity plus any member u of v is just equal to u. The existence of a vector additive inverse. For every, again, this will be a unary operator. It will take members of v to members of v. And so for every u in v, there exists another element denoted by minus u of v, such that u plus its additive inverse is the additive identity, and so it's a right additive inverse. And by commutativity of addition, the additive inverse of u plus u is the additive identity. Next, we also have an operation called scalar multiplication. And so there exists some operation taking the Cartesian product of the field with the set V to the set V. And so scalar multiplication distributes over vector addition. If there is an element C of your field, and then for any element C of your field, for any elements U and V of the vector space V, we have that the scalar C times the sum of the vectors U and W is equal to the vector sum of the scalar product of the scalar C with the vector U added to the scalar product of the scalar C times the vector W. Scalar multiplication distributes over scalar addition. Let C and D be members of your scalar field. Let U be a member of your vector space V. Then the scalar addition of the scalar C and D having a scalar multiplication, being scalar multiplied, scalar multiplying U is equal to the vector sum of the scalar C and the vector U added to the scalar product of the scalar C and the vector. That's wrong. Okay, try that again, because that's wrong. The scalar product of the scalar sum of the scalars C and D multiplying the vector U is vector sum of the scalar product, the scalar product of the scalars C with the vector U added to the scalar product of the scalar D and the vector U. The associative property for scalar multiplication. So let C and D be scalars and U be a vector. Then the scalar product of, So the scalar product of C times the scalar product of D. Okay, so let's start this over again. So the scalar product of the scalar C times the scalar product of the scalar D times the vector U is equal to the scalar product of the scalar multiplication of the scalars C and D multiplying the vector U. The existence of a scalar multiplicative identity. So again, this will be a unary operator going from the empty set to the scalar field F. There exists an element of the scalar field F, and we'll denote that element by 1, such that for every vector in your set V, I have that the scalar product of the scalar identity 1, and so this is my scalar identity, times the vector U is just the vector U. If a set satisfies all those conditions over some field F, then we say that it is a vector space. Now, if a set satisfies all of these same properties, all these 10 properties, and the scalar field is not a field, it's a ring, so it's a scalar ring, then we don't call it a vector space, we actually call it a module. We may or may not use this in the future. Probably we won't, and if we do, we'll probably only use it in one fleeting sort of comment that I might make. Okay, so vector spaces, and most of the time we'll just be looking at Rn, or many times just R2 or R3. So, okay, so notation. So let me give you some notation on how fast things grow, how quickly things decay. And so the little o and the big O notation. So let me give you those. So first, big O. So this is not 0, it's a big O. Okay, so F is a member of the set of big O's if F at 0 is 0 and there exists some neighborhood of 0 and there exists some C greater than 0, such that for all vectors X in your neighborhood of 0, actually that's really a vector 0. For all X in your neighborhood, we have that the norm of f of X is less than or equal to that constant C times the norm of X. Of course, X is in the vector space. Oh, I didn't say F here. Where is F going from? F is going from V to W. Okay. So here, X is in V, and so this norm here is the norm that the vector space V has. And f of x is in W. So this norm here, space W has. So there's actually a terminology for this. So if f here satisfies this condition, you know, that f is 0, 0, and f of x is less than or equal to the norm of f of x is less than or equal to c, some constant c times the norm of x. If that holds, then we say that f is Lipschitz continuous at 0, at the origin. And so this is named after, obviously, Lipschitz. So such a function is called big O. And so a lot of times the notation we give is f is a member of big O of VW. So now little o. So that's big O. So now let's look at little o. So maybe I should. Just in case people didn't notice this is changing. Okay, so let's do it in red. So the big O is in black definition. Let me give you the little o notation. So f is a member of little o, the set of all little o functions. So notice this was a big O and this is now a little o. If f of 0 is 0 and the limit as x goes to 0 of the norm of f of at x divided by the norm of x is 0. And so, and of course, this is a number because these are norms. So this is just some number. So such a function is called little o. So we say that f is a member of little o of VW. If you don't know, so if you know what the vector spaces are, then we just use this notation. So if we really want to tell you what your vector spaces are, then we use this notation. Okay. Because maybe, well, we want to be explicit and tell you what those are. So what you'll notice is a lot of times they'll just say, oh, and they won't tell you what the vector spaces are because it's understood in context what they are. So note the following. I have that if f of x is equal to x, then f is big O, because obviously the norm of x is less than or equal to the norm of x. So in this case, my constant c, just let it equal 1. Okay, so certainly f is in big O, but it's not little o. If you do f of x, which is x, divided by x, well, that's just x, then they, you know, in norm, well, it just can be x's, absolute value of x's, they cancel, so you get 1, and so the limit as x goes to 0 is not 1, therefore f is not in little o. So f of x equaling x gives me a function that is big O, but not little o. If you had something like x to the 3 halves, well, then I have that as x goes to 0, this thing here, the norm of f, x to 3 halves, over the norm of f, which is x to 3 halves, over the norm of x, which is x. Well, you cancel those, so that's x to the 1/2. Well, the limit as x goes to 0 is 0. So f is little o. And so, well, if f is little o, then it's big O. You can, if it's little o, then you can just let this certainly be a true statement. Or then this will be, it'll be Lipschitz continuous at 0. Okay, so note, that's what I'm saying, that if something is little o, then it's big O. So little o of VW is a subset of big O of VW. Similarly, all linear transformations are big O. You can just let the constant be 1. So HOM of VW is a subset of big O of VW. So if F is big O, then we write f of x as equaling big O of x. So a lot of times you'll see that we'll do some sort of notation where I'll say that, that we have some equation, and then at the end I'll say plus big O, meaning that somehow the remaining part is Lipschitz continuous at 0. It goes to, or it's little low, meaning that it approaches 0 very fast, approaches faster than x equaling 1. Okay, so matrices. So many of the things that we'll be doing involving derivatives, actually and integrals too, will somehow involve matrices. And so just to recall, and this is a quick sort of recollection of matrices, and if you haven't taken linear algebra, this will be sort of a Reader's Digest version, a Sham's outline sort of condensed version of the minimum you have to know matrices. Let n sub n equal just the set 1, 2 to n. Let n superscript m subscript n be the Cartesian product of m of these n sub n's. Then the set m sub m cross n, sometimes they write this as mn. So, and this is horrible, so that would not be 12, that would be 1, 2. And so I usually put a cross product. I may or may not put a cross product in between them, so you notice that they're differing numbers rather than thinking it's 12 or something. Okay, so m sub m cross n is the set of functions f from n superscript m subscript n. So what this means is that this will be oh wait, these have to be Cartesian products. Oh, This was wrong. This was wrong. I wrote something wrong. Okay, so this is the notation. Sorry about that. Is it m by n? Yeah. Okay, so this is the set. Oh, good. Okay, so m sub m cross n is a set of functions from the Cartesian product of m, the first m natural numbers, cross the first n natural numbers. Okay, that makes sense. The other one didn't. Okay, so, and this will be taken, and this will go to your field, whatever your was. So this is called the set of m by n matrices. So we can use an array to represent a matrix. Linear combinations. Let V sub j be a member of the vector space V over this field F, and let A sub j be a member of the field F. Then the vector, the sum of AJ, VJ, is called a linear combination of the vectors VJ. And so, you know, if you have two vectors, then I guess I should make them into vectors. If you have two vectors, then their linear combination is just the sum. And that's all I'm saying. A basis of a vector space, a subset B of a vector space V, is called a basis for the vector space V if every vector in V can be written uniquely as a linear combination of vectors in the base B. This basis B. The number of vectors in the basis B is called the dimension of the vector space V. It turns out that every vector space has a basis if we assume the axiom of choice. So this is one of the strong reasons that people want the axiom of choice to be true, or to make that as an assumption for our definitions. However, not every module has a basis. So if you're just dealing with a vector space over a ring, not a field, then it may not have a basis. And again, remember, vector spaces over rings are called modules. Recall, oh, that's what it says. Recall that we call a vector space over a ring a module. Of course, when I say vector space, I mean a set that satisfies all those 10 properties that I had for a vector space to hold, for them, you know, that they would need to hold in order to be a vector space. Okay. There is a correspondence between linear transformations and matrices. And so that's really sort of the whole idea behind linear algebra, is that somehow linear transformation and matrices There's some correspondence. Well, for finite dimensional vector spaces, if you have a finite dimensional vector space, then a linear transformation has some sort of representation as a matrix. So let me, again, I'm just doing a very quick overview of this. Whatever, basically giving you the necessary facts that we'll need in order to look at things that we need to define integer. Let U, V, W be vector spaces over some scalar field F. Let C be a member of this scalar field. Let S, T be linear transformations from the vector space U to into the vector space V. Then the scalar multiplication of C times the linear transformation T is a linear transformation from the vector space U to the vector space V, where, well, this is defined in the obvious fashion. You just define it as C times T. So you do T of U, T of, say, let U be a member of the vector space big U. Then T of U will be some member of the vector space V. Define C times T as being C, the scalar multiplication of C times T of U. And since V is a vector space, scalar multiplication is defined. And so if you define it in that obvious fashion, then this C of T is a linear transformation. Similarly, S plus T is a linear transformation from the vector spaces U into the vector space V. Let S be a linear transformation from the vector space U into the vector space V. Let T be a linear transformation from the vector space V into the vector space W. Then T composed with S is a linear transformation from the vector space U into the vector space W. And we'll give you a representation in about 2 seconds. If T is a bijection, then we actually call T a linear isomorphism. And so T inverse exists because it's injective. Well, because it's a bijection. And it's a linear transformation from the vector space, well, W back to the vector space V. So here it is, W back to the vector space V. And so if T is a isomorphism, then a linear isomorphism, then T inverse is a linear isomorphism also. If V and W are finite dimensional, it turns out that then the dimensions of V and W will be the same if they're isomorphic. Let V be an m-dimensional vector space. If it's an m-dimensional vector space, it has a basis, V1, V2, up to Vm. Then given any vector, U1, U2, all the way up to UM in W, there exists exactly one linear transformation T from the vector space V into the vector space W, such that T of VI is equal to WI. So there is a way to just go from members, if you take any set of vectors in your vector space, then there's a way to transform from from your basis into a member of, into one of these M vectors. When V and W are finite dimensional vector spaces, there is a linear isomorphism T and a matrix A, where T is defined as multiplication by A. And so there is an isomorph, basically there, for any linear transformation T between finite dimensional vector spaces, there corresponds some matrix A. And let me say more about that. There. So let me tell you more how it's defined. Now, I could either do right or left multiplication. For some reason, I did it as a left multiplication. I usually like right multiplication, but I don't know why I did it as left. Oh, just because of the dimensions, I had to make it, do it that way. Let T be a linear transformation from the vector space V into the vector space W. And let these be finite dimensional vector spaces. So let V be a M dimensional vector space, and let W be an N dimensional vector space. Then T can be represented by M by N matrix. So this has a dimension M, and it's the same as the number of, let's see, that's rows. Yes, the number of rows of the matrix. And W has a dimension N, the same as the number of columns of your matrix. So I have some matrix, some M by, then let V okay, 1 second. See if I can get control back. Okay, 1 second. There. Yes. So let V be a 1 by M matrix representation of the vector V. Since V here, the vector space V here is M dimensional, then the linear transformation T evaluated at this vector V in the vector space V is just the matrix multiplication of the vector V and the matrix A. And it's really sort of nice. Now we'll be able to tell you that these linear transformations are just sort of matrices, sort of. Or they can be represented by matrices. So let S be a linear transformation from the vector space V into the vector space W. Let T be a linear transformation from the vector space V into this vector space W. And let S have matrix representation A, as we had above. And let T have matrix representation B. Then S plus T, the linear transformation S plus T that we told you existed like 2 minutes ago, has matrix representation A plus B, and we define it as the matrix where the ijth entry is A sub ij plus B sub ij, where A sub ij is the ijth entry of the matrix A, and B sub ij is the ijth entry of the matrix B. Similarly, the scalar C, so let C be a member of the scalar field F. Then C times S is the linear transformation that has a matrix representation of C times A, where the ijth entry of CA is C times A sub ij, where A sub ij is the ijth entry of the matrix A. And so this is the matrix representation of the linear transformation CS. If S is an invertible linear transformation, meaning that it is a linear isomorphism, so meaning that it is a linear transformation that is bijective. I guess I should say that some authors will say that you really only need, rather than bijection, you need injection. But I will do bijection because it will make, even though I usually only want injection, I will say that I want bijection because it makes my life much easier in the future. And so that's why I required bijection. For a linear isomorphism, bijection is always necessary, but in order to have an inverse, I will say that it needs to be bijective. So if S is an invertible linear transformation, meaning it's a linear transformation which is bijective, then A inverse is the matrix representation for S inverse. And whatever the inverse, however you can, find an inverse of a matrix involves a lot of steps. But however you found the inverse of a matrix, that thing that you find will be the matrix representation for the linear transformation S inverse. Oh, so we're almost up to where I can say what a derivative is. Okay, so this is the background before I even started. So this is sort of the step 0 before I get to step 1. And it'll be like 2 or 3 before I can even get to tell you what the derivative is. So let S be a linear transformation from the vector space V into the vector space W. Let T be a linear transformation from the vector space W into the vector space U. For T composed with S, recall that T composed with S will be a linear transformation from V to W to U, from V to U, is matrix multiplication. So composition of linear transformations corresponds to matrix multiplication. So it'll just be B times A. And this is why, so B times A is the matrix where the ijth entry is the sum of B sub ik times A sub kj, where A sub ij is the ijth entry of A, and B sub ij is the ijth entry of B. And so this gives you, where you sum here, I haven't told you, you're summing from k equal 1 to the dimension of W. So whatever the dimension W is. Say K equal 1 to P. Where P here is the dimension of W. Okay. Derivative. So before I can tell you what a derivative is, I have to first recall what we did in the one-dimensional case, of what we did in the one-dimensional case. So as I said at the top of the hour, a derivative is the best linear approximation to a function. Okay. Now, let's see what we did back in Calc 1. So suppose you have some function, y equal f of x. And suppose I have a tangent line to y equal f of x near the point A. So here we're going to have, notice in my recollection, I did say, I should have said, because saying near, I should have said, because this is actually better to say this way. The derivative is the best linear approximation to a function. Let's not say near a point, because that will be a sticking point. Okay, so let's see how far down I gotta go. Let's go further. That's too far. Here I am. So y equaling f of x. This is the graph of y equaling f of x. This line represents the tangent line to y equal f of x at the point x equal a. It is the best linear approximation to the function y equal f of x near the point x equal a, and it has a slope denoted by, let's say, f prime. So let me give you some further notation. So usually the way that we look at the slope of the tangent line is we say, well, let's approximate it by the slope of the secant line. And so to do that, we usually say, well, let's start at some point A and go a little ways away from it. So let's say A plus H, where H here is some small quantity. And I want to look at the slope of this line and have it approximated by the slope of the line through this point and through this point. So this will have coordinates a plus h, f of a plus h. This will have coordinates a, f of a. And so this distance here, f of a plus h to f of a, I'll denote that by the change in y. Okay, this will be, if I want to find the slope here of this line here, it'll be the change in y over the change in x. I'll call the change of x h rather than delta x. And so this is the change in y, delta y. I'll denote that by, well, the change in f, evaluated the change in f at a, and the change in f is, well, where x here varies by h. So the delta y here is really a function of h. So if you had a fixed f and a fixed A, then this change in y would depend on h. How close are you to A? And so I'll denote it delta f sub A at h. Well, we can think of this change in y as being two parts. Well, what you really want and your error. So this is what I want. And what I want is, well, I'll call it d, the differential of f at A, and it'll be a function of h. If I look here, this will be the slope of the tangent line, and it'll be a function of, well, h, how far you've gone out. And so this will just be h times f prime at A. It's by, oh, here it is. It is looking at similar triangles. If I go a distance of 1 in x, the distance I go to get to this tangent line is denoted by f prime, the slope of the tangent line. And so if I instead go h in x, then this will be h prime, h f prime at A. And so this h f prime at A, I'll denote by d, the differential of f sub A at h. So that is what we want. This is our error between the secant, our approximation using the secant line and our approximation and the actual answer that we want using the tangent line. And so this error is just, well, this whole guy, the delta sub f, delta of f sub A at h, minus this guy. So it's this minus this, which is d of f sub A at h. And I want it to be small. I want it to be little o of h. And so let's see that that is really what we want. And so let me try to convince you that I want this to be little o. And that gives us our definition of derivative. So let's show that. Well, the limit. So to show that this is little o, I want that this in absolute value divided by h to go to 0 as h goes to 0. And so I want that this over h goes to 0. So I want the limit as h goes to 0. Note that if this goes to 0, so does its absolute value. I want the limit as h goes to 0 of delta f sub A at h minus d of f sub A at h divided by h. I want that to be, well, 0. And so let's see if it is. Let's write delta f. Well, by definition, delta f sub A at h is f of A plus h minus f of A. And df sub A at h is h times f prime at A. And so this translates into the limit as h approaches 0 of the quantity f of A plus h minus f of A minus h f prime of A all over h. If f is differentiable, then, meaning if each of these quantities exist, each of these limits exist, then I can take the limit of each and see what it approaches. And so this is just a limit as h approaches 0 of f of a plus h minus f of a over h minus the limit as h approaches 0 of, well, h is canceled. The limit as h approaches 0 of f prime at a, which is just f prime at a. But the limit as h approaches 0 of f of a plus h minus f of a over h, well, that's just f prime. F prime minus f prime at a is just 0. And so that says that this quantity, delta f sub a at h minus d of f sub a at h, is little o of h. And so, delta, and maybe I'll write it. I should f. Let me write a better delta. Sub a at h is equal to d of f sub a at h plus little o of h. Okay, so I have shown that this occurs when f prime is your slope of your tangent line. So this is this is really the definition that we had for the derivative. Now let's look in more than one dimension. So now what I'm going to do is, well, I have some curve here, z equaling, so this is the graph of z equaling f of x, y. And let's look at some point here, A. Then let's look here at the plane that best approximates this surface z equaling f of x, y near the point x equal a. Okay, so this is best that I can do. Let's see if you, so let's go out a distance h from the point A. Oh, that almost looks like that's a, here, let's, okay. So let's go some, so this is some point A here, and let's go h, a distance of h in any sort of direction. So let's say that now we're at some point over here. On the tangent line, on the tangent, let's say that this is some point, and say that this is another point on the actual surface we're talking about. Then this distance here is delta f sub a at h minus d of f sub a at h. And we'll want that this is little o of h. So, 5 minutes. Okay. Differentiable. Let V and W be norm linear spaces of norm linear vector spaces, and let N sub A be a neighborhood F, maybe I'll use since it's a vector, maybe I'll use that notation. F from this neighborhood of A into which will be a vector space, this vector space into the vector space W is differentiable at A. Now, of course, these vector spaces are assumed to be complete vector spaces. Which actually a complete vector space, we assume we call those Banach spaces. Okay, so let V and W be norm vector spaces. Let N sub A be a neighborhood of the vector A. F from V to W is differentiable at A if there exists some linear transformation from the vector space V into the vector space W, denoted by D at F sub A, and it is such that the change in F sub A at H is equal to D at F sub A at H plus little o of H. This D at F sub A is called the differential of F at A. It is the unique bounded linear transformation to delta F at F delta F at A. And so, a bounded linear transformation is a linear transformation which is bounded, meaning that the norm of this transformation is less than or equal to some constant for all vectors in your vector space. So let me give you, so this is the derivative, this object here. The Frechet differential. Ooh, I have 1 minute. Okay, so I better stop here because I do not, well, wouldn't you know that I'm just coming up upon actually giving it in Rn. Okay, so I'll have to end it here and we'll have to continue tomorrow. Okay, so let's stop here. So let me give you the idea of differentiability. So let V and W be complete norm vector spaces. And actually, why am I calling it a linear space? That's the same as a vector space, but let's call it a vector space. Let V and W be a complete norm vector space. And let N sub A be a neighborhood of A in this vector space. Let F be a linear transformation from the vector space V into the vector space W, taking some open neighborhood of A into W. This mapping, this linear transformation, well, this function, sorry, not linear transformation, this function will be differentiable at the point A if there exists some linear transformation D F sub A, which is a member of Hom VW, meaning it's a linear transformation from V to W, such that the change in F is equal to dF plus little o of H. dF sub A is called the differential of F at A. It is the unique bounded linear approximation to the change in F. The Frechet differential. Let V and W be normed vector spaces, complete norm vector spaces, and let N sub A be a neighborhood of A in the vector space V, and let F be a mapping from this neighborhood of A into the vector space W. Then F is differentiable at A if there exists a linear transformation from V to W called, and let's denote it by D F sub A, such that the limit as H approaches 0 of, and I guess maybe I'll put a subscriptive V here, the limit as H approaches 0 of delta F sub A at H minus dF sub A at H over the norm of H is 0, where this 0 vector is in W, this norm is the V norm, and this 0 is in V. In the case that V is R M and W is Rn, then the matrix representation of this differential, dF sub A, is called the Jacobian matrix of F at A. And in this case, we have the limit as H approaches 0 of the norm F at A plus H minus F of A minus dF sub A H is 0. This matrix J is such that dF sub A at H is equal to J times H. Now, depending on how you want to define H, it could either be on the right or on the left. And this, I sort of like it on the left, even though occasionally I put it on the, well, actually I like it on the right more. Occasionally I'll put it on the left. And so J here, again, is called the Jacobian matrix. In the case that V is Rn and W is R, the matrix representation of dF sub A is a vector called the gradient of F at A. And it's denoted by this nabla F sub A. Sometimes we call this del, but it's the nabla symbol. So this is the nabla symbol. Sometimes we just say this is del F sub A. So in this case, we have that delta F sub A at H, the change in F at A, is del F sub A, the gradient, dot, and this is will actually be the dot product, h plus little o at h. Writing this delta f out, this is f a plus h minus fa is equal to this gradient del f sub a dot h plus a little o. In section 14.6, we'll be talking about the directional derivative, but let me just sort of slightly introduce it in this section. So let f go from Rm to Rn. Let u be in Rm, but not equal to 0. Then let's define the directional derivative in the direction of u of f at a to be the limit as t goes to 0 of f evaluated at a plus tu minus f of a all over t. In the following, we will see that differentiable functions are continuous. Composites of differentiable functions are differentiable. Differentiability of f at a implies the existence of all directional derivatives of f at a. However, the existence of all directional derivatives does not imply differentiability. So even though you may have all directional derivatives, this doesn't mean that your function is necessarily continuous, differentiable. Next, differentiability does not imply continuity. I'm sorry, I said it the wrong way. Continuity does not imply differentiability, nor does the existence of all of your partial derivatives imply differentiability. So there is a relationship between differentiability and the fact that there are derivatives. A function is differentiable, then the gradient will just be partial derivatives. The Jacobian matrix will just involve partial derivatives. And so if a function is differentiable, then the matrix representation of the derivative will involve partial derivatives. But merely having the existence of partial derivatives, this will not imply, nor continuity, this will not imply the fact that the function is differentiable. Okay, so the tangent plane. So when we were looking at the derivative in calculus 1, we usually think of, well, the derivative is the slope of the tangent line. Well, problem is in more than one dimension. What does it mean to be a slope? You know, there's obviously, you know, there's not one slope. There's not really one direction to look at. So that makes no sense to say derivative is a slope of a tangent line. And of course, in more than one dimension, a line becomes like a plane. And so the concept of a tangent plane will be defined. So let's look at, in this particular case, the case where we have a function going from R2 to R. And let us try to describe the tangent plane. So suppose f goes from R2 to R, and suppose it is differentiable and has continuous, and this will be important in the future, has continuous partial derivatives at x0 and y0. Then the equation of the tangent plane to the surface y equal f of x is z equaling f at x0, y0 plus the gradient of f, the vector f partial of f with respect to x, partial of x with respect to y at x0, y0 dot x minus x0 comma y minus y with 0. And so the z minus f at x0, y0, this is just a change in f. And this is the derivative of f sub a, well, sub x0, y0, dot, in this case, this is my h, basically. And so I can also write this, well, I'll multiply out the dot product. And so z equals f evaluated at x0 comma y0 plus the partial of f respect to x at x0 y0 times x minus x0 plus the partial of f respect to y at x0 y0 times y minus y0. That is the equation of my tangent plane. And so this is the equation of my tangent plane that you should know. Affinization. And so let f go from R2 to R, then L xy equaling FAB plus partial f respect to x at AB times x minus a plus partial of f respect to y at AB, y minus b. This is called the linearization of f at AB. And so this previous thing that we looked at as the tangent plane, this part here is called the linearization of f at a. So f of x, y is approximately equal to its linearization, L at x comma y. So again, this is called the linear approximation or the tangent plane approximation to f near the point AB. So note, and this is sort of due to historical reasons, this affine approximation is called a linear approximation. So even though in reality this is not a linearization, we could say it's linearization. It's because, well, if you brought the f a comma b to the left-hand side, then this would be a linearization. So it's just that we sort of translated it by a constant. And so it's an affine transformation, not a linear transformation, but people still call it the linearization. Due to the historical unfortunate events that we call, like in, college algebra and elementary, intermediate algebra, we call lines rather than affine transformations. So y equal mx plus b, that is not linear, but we call it a line. So it's an unfortunate sort of historical bad terminology. We should have changed the name of line or something, or changed the name of linearization to something different. Okay, so differentials. Oh, this is just differentiability. So this is the definition of differentiability in your book. And so I'll give you their notation. If f goes from R2 to R, and z equal f of x comma y, then f is differentiable at AB if, well, this is sort of my notation, or the usual, I wouldn't say my notation, it is the usual notation that is given. Delta z is equal to df sub AB evaluated at delta x, delta y, plus the low of delta x, delta y. And so let me write the matrix representation for this linear transformation. So delta z equals del f at AB dot the vector x comma delta y plus the low of delta x delta y. Okay. And well, this is really little o of delta x delta y. And so that's the little o of it. In your book, they give a little bit looser of a definition. So they say, and this is their notation, delta z is equal to, well, let's write out. So I have the matrix representation here, and the matrix representation turns out to have components, delta f, delta, well, the partial of f respect to x, comma, partial of f respect to y. And so doing the dot product, we have that delta z is equal to partial of f respect to x at AB times delta x plus partial of f respect to y at AB, delta y plus epsilon delta x plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 goes to 0 and epsilon 2 goes to 0 as delta, the point delta x comma delta y goes to the point 0, 0, 0 comma 0. So so even though a function that's continuous is not necessarily differentiable, we have that if and the existence of partial derivatives does not imply differentiability, we do have that if the partial derivatives exist and are continuous, then that will imply differentiability. And so let's do this, state this in the case R2 to R. And so, and this is a theorem in your book, if f is a function from R2 to R, and if the partial of f respect to x and the partial of f respect to y, if these exist near the point AB and are continuous at AB, then f is differentiable at AB. So this gives a partial result telling you when a function is differentiable. The differential. Let f go from Rn to R. Then df at h is just del f dot h. A lot of times we write dz equals del f dot dx. So in particular, Again, let's go from R2 to R. Then dz is equal to, well, del f. So the gradient of f. The gradient of f, well, this is my linear transformation, the df, the d. And so it is can be thought of sort of symbolically, containing the following operators. Take the derivative with respect to x, comma, the derivative with respect to y. Evaluate it at f dot the vector dx comma dy. So dz is equal to, so now this here is the matrix representation for df, partial f. It has components, the partial derivative of f with respect to x, comma, the partial derivative of f with respect to y, dot the vector with components dx comma dy. The dz is equal to partial, so let's just do the dot product. So dz is equal to partial of f with respect to x, dx plus partial of f with respect to y, dy. A lot of times we call this the total differential. Okay. Let's look at the case where we're going from Rm to Rn. Let f go from Rm to Rn. If f is differentiable at A, then all directional derivatives of f at A exist. And, oh, this is the notation for directional derivative. And the directional derivative in the direction of u of f at A is just equal to j times u, where j is the matrix representation of the linear transformation df sub A. This is usually called this j here, this is why it's called j, is called the Jacobian matrix. Recall that even if all directional derivatives exist, it may be that the function is not differentiable. So we have to say that both the function is differentiable and all directional derivatives exist. We can't drop one of those conditions. Let f go from Rm to Rn. Let this be differentiable at A. Then f is continuous at A. And so just like in calculus 1, if a function is differentiable, then it's continuous. But every continuous function is not necessarily differentiable. And the same is the case here. And so differentiable functions will be continuous. So note that it is possible for partial derivatives to exist and for the Jacobian to exist, and yet for the function to not be differentiable. So if a function is differentiable, then, and all the partials exist, then the Jacobian exists and is equal to that differential, but not necessarily the other way around. So this leads to a quandary. In general, to show that a function is differentiable, you need to use the definition of the derivative. But as we saw in the previous, well, I guess 2 theorems ago, a partial result is given by the following theorem that will relieve you of some of this burden that you always have to use the definition of the derivative. So suppose that every first partial derivative of f exists and are continuous at every point in an open interval a. Okay, let's start this over. I'm sorry. Suppose that every first partial derivative of f exists and are continuous at every point in an open set A in Rm. Then f is differentiable at each point in A. So usually we say that a function is C1 if all of its partial derivatives exist and are continuous at every point in the set A. So this means that if we restrict our viewpoint to only look at functions that are continuously differentiable, that have functions that have first partial derivatives existing and being continuous, then the function will be differentiable at every point in that set. Okay, so let's do some examples. So let f, I'm going to do that first. Okay. Oh, okay. I want to do those first before I do this. Do this one first, and then I'll do those other two. Let's do that instead. Okay, so let's do that. On page 974, let's do problem number 2. In exercises 1 through 6, find an equation of the tangent plane to the given surface at the specified point, z equaling x plus 2 quantity squared minus 2 y minus 1 quantity squared minus 5 at 2, 3, 3. Okay. So just recall that the tangent plane at some point x0, y0, z0, that this has the following form: z is equal to z0 plus, or did I write, which way did I write? Doesn't really matter. Partial of f, z with respect to x at x minus x naught plus partial of z with respect to y. Of course, these are evaluated at x at these points, well, times y minus y naught. Okay. So in order to do this, I'm going to have to first figure out some partial derivatives. So let's figure out some partial derivatives here. Okay. So let's figure out the partial. Of z with respect to x. Okay. And so that's just going to equal 2 x plus 2 times 1. And the partial of z with respect to y, that's going to equal minus 2, bring down the 2, so that's a minus 4, y minus 1, times the derivative of what's inside, which is just 1. Okay. And now let's evaluate each of these partial derivatives at the point x0, y0, z0. So let's evaluate. At the point 2, 3, 3. And so this is the partial of z with respect to x. Let's evaluate this at the point 2, 3. Question. Okay. So note that if you plugged in 2 for x and 3 for y, you get 2 plus 2 is 4 squared is 16 minus 3 minus 1 is 2 squared, which is 4, times 2 is 8. So 16 minus 8 minus 5 is 3. And so at 2, 3, z is equal to 3. So let's plug this in. And so I have this is equal to 2 times, well, x is 2. And so this is equal to 8. Let's plug in partial of z with respect to y at the point 2, 3. And so this is a negative 4 times 3 minus 1. Oh, so that's just equal to negative 8. Okay. And so let's find the equation of the tangent line. Nope, tangent plane. At the point 2, 3, 3. So I get z minus z naught equaling partial z with respect to x. x minus x naught, partial z with respect to y, y minus y naught. Okay. And so this is z minus 3 is equal to 8 x minus 2 minus 8 y minus 3. And so I get z minus 3 equals 8x minus 16 minus 8y plus 24. And so I get z. Actually, let's bring everything to one side of my equation. So I get 8x minus 8y minus z is equal to, that would be 8 minus 11. And that is the equation of my tangent plane. Okay, let me do problem number 30. Well, that's going to be okay, I'll leave those for a second. Okay, so find the differential of the function. Okay, so let's find the total differential. So let me just write down what the total differential is. Maybe I'll insert something so I can work on that. So the total differential is, well, this involves x, y, and z. And so it's going to be the partial of L with respect to x dx, the partial of L with respect to y dy, plus a partial of L with respect to z dz. Okay. So let's try to figure that out. So I'm going to have to take some partial derivatives. So I'll have to take the partial of L with respect to x. Well, I'm going to treat x as a constant, x as a variable, and everything else as a constant. So the z e to the minus y squared minus z squared is a constant. The derivative of a constant times x is the constant. Z e minus y squared minus z squared. Okay. Next, I want to take the partial of L with respect to y. The y here is a variable, everything else is a constant. And so I have a constant times the derivative of e to any exponent is e to that exponent times the derivative of the exponent. The derivative of minus y squared minus z squared is a constant, is just minus 2y. And so this is a minus 2 xyz e to the minus y squared minus z squared. Let's take the partial of L with respect to z. Well, z is a variable, everything else, nope, z is a variable, everything else is a constant. So in this case, I'm going to have to use a product rule. And so derivative of the first times the second plus the first times the derivative of the second. E to the minus y squared minus z squared times the derivative of the numerator, the derivative of minus z squared is a minus 2, so this is a minus 2z, so this z becomes z squared. And so maybe I'll write this as follows, as it's x minus 2x z squared all times e to the minus y squared minus z squared. Okay, so now let's figure out the differential. And so I won't really need that much of here. So the differential dl is equal to partial of f with respect to x dx plus partial of, oops, no, that was correct. Partial of f with respect to y minus 2x y e to the minus y squared minus z squared dy plus, lastly, partial of f L with respect to z, x minus 2x z squared e to the minus y squared minus z squared dz. And that is your total differential. Okay, so let's do the next problem. Problem number 34. So the question is, well, what do these differentials mean practically? And so we can, just like in the case of calculus 1, we can use these to approximate. I'll bring it down a little bit. We can use these to approximate the change. And so, let me bring this up, so because I don't want to redo this picture. And yeah, I don't want to redo this picture either. Okay, if I have enough room. Okay. Okay, trying to move. Okay, let's go. Eh. Yeah, whatever. Yes, it's going to take me just as long to clean up as it would have been to actually draw this again. Okay, so let me do this problem. Okay, good. Oh. Okay, now it's cleared up. Okay, so in problem 34, use differentials to estimate the amount of metal in a closed cylindrical can that is 10 centimeters high and 4 centimeters in diameter. If the metal in the top and bottom is 0.1 centimeters and the metal in the sides is 0.5 centimeters. Okay. So let me do problem 34. Use differentials to estimate the amount of metal in a closed cylindrical can that is 10 centimeters high and 4 centimeters in diameter. So 10 centimeters high, 4 centimeters in diameter. Therefore, 2 centimeters in radius. If the metal in the top and bottom, so the top here and the bottom, is 0.1 centimeters, and the metal on the sides is 0.05 centimeters thick. So I have here that the thickness on the top and bottom is just dH. I'll denote that, and I'll be 0.01, 0.1, and the thickness on the sides, that'll be how the change in R. I'll denote that by dr. Okay, so let me do this. So I have here that H is equal to 10 centimeters. R, the radius, is 2 centimeters. So dH, the change in the height, we said was 0.1 centimeters. And dr, the change in the radius, the thickness around, is 0.05 centimeters. And so the volume of a cylinder is pi r squared h. Therefore, using differentials, I have that dV is equal to the partial of V with respect to R dr plus a partial of V with respect to H dH. And so dV is equal to 2 pi RH dr plus partial respect to H is pi r squared times, in this case, dh. And so dv is equal to 2 pi 2 times h10 times dr 0.05 plus pi r 2 dh 0.1. And so this is equal to, well, 10 times 0.05 is just 0.5. And so this first term is just 2 pi. 4 times 0.1 is 0.4. So this is a total of 2.4 pi. And so, and I'll just leave this, I guess. And so the change, the volume, is approximately equal to the differential. Therefore, the change in the volume is approximately 2.4 pi. And if you plug that into your calculator, you get 2.7.5, approximately 7.5 cubic meters of metal. And so that's how much, cubic centimeters of metal. So that's how much tin you have to use to make the can. Okay. Show that the function is differentiable by finding the values of epsilon 1 and epsilon 2 that satisfy definition 7. Okay, so let's do that. So their definition 7 says delta okay, that's nice. That's very nice. Okay, 1 second. 1 second, thank you. Okay, so that says that delta F is equal to partial F respect to X, delta X, we'll do delta X's, plus partial F, partial Y, delta Y, plus epsilon 1, delta X, plus epsilon 2, delta Y. Okay, so show that the function is differentiable by finding the values of epsilon 1, 2. Okay, so let's do that. So first thing is let's find the change in F. Okay, good. Let's find delta F. So delta F is just F at X plus delta X maybe I'll just suppress the delta X, delta Y, is F of X plus delta X, Y plus delta Y minus F of XY. Okay. Okay, What are you doing? Give me back control. Okay. Sorry. Still not responding. Oh, it's moving again. Okay. Minus f of xy. Okay, so let's compute this. And let me give you a little bit of room. Okay, so there's some room here. So this is equal to x plus delta x times y plus delta y minus f of y plus delta y squared minus, so that's this first term, minus xy, f of xy, which is xy minus 5y squared. Okay. So this is equal to okay. So this is equal to multiply this out. It'll probably have to be more than one line. So I'll just say this is equal to xy plus x delta y plus y delta x plus delta x delta y. Minus 5 y squared minus, there'll be in the parentheses, if you square this out, there'll be a 2y delta y, so this will be a minus 10 y delta y. And then you have a delta y squared, so minus 5 delta y squared minus xy plus 5y squared. Uh-oh, there's no way I can finish this. So this is equal to, let me cancel these and cancel these. Okay, so this is equal to x there's no delta x anywhere. Okay. Where is the y delta x? Oh, this is a delta x. That was an error. Okay, so it's just, so that's a x, and that's a y, and that's that. Okay, so there's a y delta x, so there's a delta x here. And there is what's the delta y's? Just x plus minus 10y delta y, okay, plus, so now these last terms, which will be, it really doesn't matter how I consider those. All these terms of x's, so I'll make that an x. Delta y, delta x, minus 5 delta y, delta y. Okay. And so this is okay, so now this is sum dot product. Okay. This is sum dot product here. Y x minus 10y dot delta x delta y okay. Get me control back. Give me control back. There. Okay, so this is sum delta x delta y plus okay, come on, please give me back control. Thank you. Oh, plus some delta y plus now we have let's say delta epsilon 1 delta x plus epsilon 2 delta y, where thank you, come on, give me back control, give me back control, thank you, where epsilon 1, this is a function of delta x and delta y, maybe I'll say that explicitly, is equal to delta y and epsilon 2 of delta x delta y is negative 5 delta y. And these have, come on, these have, just trying to do the last line, these have the property that delta x, delta 1 goes to 0 as, come on, come on, come on. Okay, this goes to 0. Okay, epsilon 1 goes to 0 as delta x, delta y goes to 0. Oh, as delta x, delta y goes to 0. Oh, come on. And epsilon 2 goes to 0 as delta x, delta y goes to 0. So I've explicitly found what the value is of epsilon 1 and epsilon 2. And this thing in here, and we'll have to just show it tomorrow, is actually the gradient. It's actually, if you look at the partial derivatives function. Okay, so that really finishes off. Oh, there's one more. So I've got to work. Yes. Okay, yeah, so I've got to, I'm cutting it off right now. Okay, so I'll just, tomorrow I'll re-show this, I guess, and just show that the, that this actually, this first term here is the gradient. But that's it for today. And so I guess I'll see you guys tomorrow. And I guess we will be able to finish off the section tomorrow. And use on date and sections. Exam number 2 is on chapter, this is 14, chapter 14. And so it will be due next Friday, and I will post it within the next, say, hour or two. Okay. Actually, no, I'll give you till Monday. So I'll give you whatever the date is, not 1 week. So not the Monday coming up, but the following Monday after that, you'll have to turn it in. Okay, and I'll put that in the instructions. It'll say for exam 2, you'll have the exam up, and they'll also have the date that it's due. Okay. Any other questions? Oh, the 13th. Yeah, that'll probably be the 13th of April. I have to look at my calendar, but something like that. That sounds correct. Yeah, like 2 weeks. Okay. I see you guys tomorrow then. Okay, bye. The amount of metal in a closed cylindrical can that is 10 centimeters high and 4 centimeters in diameter. So 10 centimeters high, 4 centimeters in diameter. Therefore, 2 centimeters in radius. If the metal in the top and bottom, so the top here and the bottom, is 0.1 centimeters, and the metal on the sides is 0.05 centimeters thick. So I have here that the thickness on the top and bottom is just dH. I'll denote that, and I'll be 0.1, and the thickness on the sides, that'll be how the change in R. I'll denote that by dr. Okay, so let me do this. So I have here that H is equal to 10 centimeters. R, the radius, is 2 centimeters. So DH, the change in the height, we said was 0.1 centimeters. And dr, the change in the radius, the thickness around, is 0.05 centimeters. And so the volume of a cylinder is pi r squared h. Therefore, using differentials, I have that dV is equal to the partial of V with respect to R dr plus a partial of V with respect to H dH. And so dV is equal to 2 pi RH dr plus partial respect to H is pi r squared times, in this case, dH. And so dV is equal to 2 pi 2 times H10 times dr 0.05 plus pi R 2 DH 0.1. And so this is equal to, well, 10 times 0.05 is just 0.5. And so this first term is just 2 pi. 4 times 0.1 is 0.4. So this is a total of 2.4 pi. And so, and I'll just leave this, I guess. And so the change, the volume, is approximately equal to the differential. Therefore, the change in the volume is approximately 2.4 pi. And if you plug that into your calculator, you get 2.7.5, approximately 7.5 cubic meters of metal. And so that's how much, cubic centimeters of metal. So that's how much tin you have to use to make the can. Okay. And so what I started last time, though, this corrects what I was doing. Okay. I was also with problem number 44. So let me go for problem number 44. Show that the function is differentiable by finding the values of epsilon 1 and epsilon 2 that satisfy definition 7. And so, in this case, f of x y was xy minus 5y squared. So, definition 7 says that a function is differentiable if there exists epsilon 1, epsilon 2, which go to 0 as delta x and delta y go to 0, such that the change in y is equal to the partial of f with respect to x times delta x plus a partial y f with respect to y delta y plus epsilon 1 delta x plus epsilon 2 delta y. And so we just looked at delta f, and we saw, and we tried to see, can we determine these values? Well, actually, I didn't even take the partials. I just said, well, using algebra, can I determine some quantity times delta x plus some quantity times delta y plus some epsilon times delta x, some epsilon times delta y. And so I just did the algebra. So delta f, the change in f, was f of x plus delta x comma y plus delta y minus f of xy. So I replaced x here by x plus delta x, y by y plus delta x, y by y plus delta x. And then I just rewrote f of xy. Multiplied each of these terms by x, so xy, x delta y, y delta x, and a delta x delta y. Minus 5 times, well, this will be a y squared plus 2 y delta y, so negative 5 times 2 becomes a negative 10 y delta y plus 5 delta y squared. Changing all the signs here, you get a minus xy plus 5y squared. So the xy's and the 5y squares canceled. Now you notice that I just have first order terms of x delta y, y delta x, minus 10 delta y. The other terms, this delta x, delta y, and the minus 5 delta y quantity squared were both not of first order, they were of second order in delta. And so let's collect all the terms that are in first order in delta. And so the only term involving delta x that's of first order is y delta x. The only term that's of first order in delta y is x minus 10y delta y. And now I have two terms here. And those are both terms that are quadratic. They are not first order in delta. And so let me just write those. Now, I could have, if I wanted to, just written this as everything times delta y, and that would have been fine. So I could have written this as delta y times delta x minus 5 delta y. In which case, then my epsilon 1 would have been 0, and my epsilon 2 would be this delta y. This would be my epsilon 2. And everything would have worked fine. I just, for some reason, chose that, well, I want an epsilon 1 and an epsilon 2. So note that my choice of epsilon 1 and epsilon 2 a little bit arbitrary. I could have chosen it differing ways, but I decided to choose it this way. Since this involves delta x and delta y, I'll factor out a delta, and this is the only thing that involves delta x. I'll factor out the delta x here and have this as a delta y, which will become my epsilon 1. Lastly, I have a negative 5 times delta y quantity squared. So I can factor out a delta y. So this becomes a negative 5 delta y times delta y. So I can call the negative 5 delta y my epsilon 2. I note that this term, this first term here, well, the y delta x plus the x minus y times the delta y is really just a dot product of the vectors having components y, 10 minus x minus 10y, dotting the delta. Okay. And so I notice that these terms go to 0 in first order in delta, whereas these terms go to 0 in delta faster than first order. In this case, well, they're second order. So, as before, I let epsilon 1 be this quantity in front of delta x, which is in this case delta y, and I let the epsilon 2 be this quantity in front of delta y, the negative 5 delta y. And obviously, as delta y goes to 0, each of these terms go to 0. And so epsilon 1 goes to 0 as delta x, delta y go to the origin, and epsilon 2 goes to 0 as delta x, delta y go to the origin. And so, maybe I'll just sort of state this. So therefore, f is differentiable, and in the notation that I gave you, this says that the differential at xy, I'm going to do it as a point, at the point xy, evaluated at delta x, delta y, is the dot product of the vector y comma 10 x minus 10y dot the vector delta x, delta y. So now, notice that we didn't do anything involving partial derivatives We didn't partials. We didn't do any sort of calculus, but the calculus came out. So let me just sort of state that, how it sort of magically came out. So since the change in f, and let's do it as a point, at the point xy, evaluate at delta x, delta y, is defined as the change in f of x plus delta x, comma, y plus delta y minus f of x, y. Well, we did all the algebra up here. We found that it was equal to y delta x plus x minus 10y delta y plus, in this case, I'll call it epsilon delta x plus epsilon delta y, where the epsilon 1s and the epsilon 2s went to 0 as delta x comma delta y went to the origin. And so, as above, I could write this as a dot product. So this is the dot product of the vector y comma x minus 10y dot the vector delta x delta y. And then this last term is just some epsilon 1 comma epsilon 2 dot delta x dot delta comma delta y. So this, since this term here goes to 0 as the delta x comma delta y goes to 0, this means that this last term is little o of delta x delta y. But if you look here, yes, okay, let me see if I can, someone accidentally did that. Oh, well, I can't get that off the screen. 1 second. Let me get you off the screen for a second. Oh, I can't. I wonder why. Okay. Don't know why that went. Okay, so why are you showing me this? Okay, I don't know why it is showing me that. And I can't seem to get it off the screen. Okay, so, oh, that's so weird. Now I can get it off the screen. Okay, sorry about that. Okay, so if I look, this delta f of, let's say at A, evaluated at, I usually call this H, is just, well, a linear, if this is a linear transformation, that's a linear transformation, plus little o. So therefore, in my notation, this is df at xy evaluated at delta x delta y. Oh, good, I'm back. This is just equal to the dot product of the vector y comma 10 minus y dot delta x delta y. Oh, let's see if I can do a little, let's see what that, I hope that means people can still hear me. Oh, okay, no problem. That was no problem at all. That was, okay, so, okay. Just computer problems. Okay, so therefore, the matrix representation of the differential is just the y, the vector y comma 10 minus x comma y comma x minus 10y. And so, So we also have, and note, that, well, let's take the partial. So let's actually do some calculus. So if I take the partial derivative of this function with respect to x, well, this is going to be 0 because it involves y. And so the partial of this with respect to x is just going to be y. And the partial of this with respect to y, well, this will just be x minus 10y, which should sound familiar. And so the partial of f with respect to x is y. The partial of f with respect to y is x minus 10y, these components of that vector. So therefore, the matrix representation of the differential is just the partial derivative of f with respect to x at the point xy, the partial derivative of f with respect to y at xy, and so we can see that this gives us just the gradient. So this is what we call the gradient. It's just the gradient of the function. And so even though the derivative really didn't involve partial derivatives or anything else, it was just some sort of algebraic quantity that we did, it turns out that it really, that the calculus part of it, the partial derivatives and all that, actually did give us that matrix representation of the derivative. And so in this case, and if the function is differentiable, then the matrix representation of the derivative will involve those partial derivatives. Okay. Okay, so let's do this. Well, I want to show that f is continuously differentiable at the origin, yet the mixed partials for the, so show that f is continuous, continuously differentiable, yet the mixed partials are unequal at the origin. Okay, and let's do this for the following function. Okay, so let's find the mixed partials. And we'll actually do that. So let's find first the partials. Okay, so let's determine the partial derivatives. So let's determine the partials. And so, and then what we'll notice also, then, therefore, it's differentiable at the origin. Okay. So first, let's find the derivative of this where we're not doing it at the origin. And so let's not do this at the origin. So partial f respect to x is equal to, and let's assume here that we're not at the origin. So it'll be the derivative. I have to use a quotient rule. So derivative of the numerator. Actually, let me write it this way. It'll be easier if I write it this way. This will be x cubed y, and this will be an x y cubed over x squared plus y squared. Okay, so let's do that. Okay, so this is going to be the derivative of the numerator, negative 3x squared y minus y cubed times the denominator. Okay, x squared plus y squared minus the numerator, x cubed y minus xy cubed times the derivative of the denominator, 2x, all divided by the denominator squared. So this is equal to, let's multiply this out. It's probably going to be longer. Let's multiply this out. Okay, so this is equal to 3x to the 4 y minus 3x to the 2 y to the 3 minus x to the 2 y to the 3 minus y to the 5. Multiply negative 2x inside the parentheses. Negative 2x 4y. Negative negative may become positive. 2x to the 2 y to the 3 over x to the 2 plus y to the 2 to the 2. So this is equal to, okay, let's see, 3x to the 4 y minus 2x to the 4y, x to the 4y. Negative 3x squared y cubed plus 2x squared y cubed is minus 2x squared y cubed minus y to the 5th over x squared plus y squared squared. Let me just check. 2, 3, 2, 3, 5, 4, 1, 2, 3. Okay, so good. Let's look at the partial of f with respect to x at the origin. Okay, so let's take that limit. And so this will equal limit as h goes to 0, f of h, I'll say 0 plus h, 0 plus h, 0 minus f of 0, 0 over h. Okay. Well, let's just see if that first part is correct. I have a plus 4. Let me just check something. That's a plus. Okay, that's a plus. That's a plus. That's a minus. That's a minus. That's a minus, and that's a plus. Okay, so that term was wrong. Okay. So that's going to be 3. 2 plus 2 is 4. Okay. Good. Good so far. Okay. That's assuming that that one's correct. Who knows what that, if that little cheat sheet there is correct, however. So this is equal to limit as h approaches 0 of, it's x cubed y. Yeah. So x cubed y minus x y cubed over x squared plus y squared minus f is 0, 0, and that's 0 over h. So this is the limit as h approaches 0. This is just 0 in the numerator, so 0 divided by h squared is 0, minus 0 is 0 over h, which is 0. And so the limit as h goes to 0, 0 is 0. So therefore, what I've written here is correct. So that is correct then. Well, whatever. Okay, so therefore, I can't copy it. Partial f, partial x is equal to x to the 4, y plus 4, x to the 2, y to the 3, minus y to the 5th over x squared plus y squared. Squared if we are not at the origin. And it's equal to 0 if we are equal to the origin, if we are at the origin. Okay, good. So that's the first part. Let me do the second part, or the second partial. So let's take the partial of f with respect to y, and let's do this not at the origin. So this is equal to, let me cheat for 1 second. It's harder to do this if you're not doing it at a board because I can't see what I'm differentiating. Okay, so I'll just leave it there. So it's equal to the numerator x cubed minus 3xy squared times the denominator x squared plus y squared minus the numerator x cubed y minus x y cubed times the derivative of the denominator 2y, all divided by the denominator squared, plus y squared squared. Okay, good. So I don't need that anymore. Okay, so let's multiply. X cubed inside the parentheses, x cubed y squared plus, why did I do that? Don't know. X cubed times x squared is x to the fifth plus x cubed y squared minus 3 x cubed y squared minus 3 xy to the 4. Multiply negative 2y inside the parentheses, negative 2x cubed y squared plus 2x y to the 4 divided by x squared plus y squared squared. There's no x to the fifth term. X cubed y squared minus 3 minus 2 is minus 4 x cubed y squared minus 3 xy to the fourth plus 2xy to the fourth minus xy to the fourth over x squared plus y squared squared. Let's see, it's down here. And it looks the same. Okay, so I don't need these sheets anymore. I can get rid of those. Okay. I was just, in case my signs were wrong. Okay, so which one of them was? Take the partial of f with respect to y at the origin. Oh, this is the limit as k approaches 0. F of 0, 0 plus k minus f of 0, 0 over k. I wonder if I still have this in mind. Yes, I do. Okay, so this is equal to, there's some stuff here. Okay, so this is equal to the limit as k approaches 0. Replace x by 0, y by k. 0 cubed times k minus 0 times k cubed over 0 squared plus k squared minus f of 0, 0, which is 0, all divided by k. So this is equal to limit as k approaches 0. The numerator is 0 over k squared is 0 minus 0 is 0 over k. And so limit as k goes to 0, 0 is 0. And so the partial I won't ever remember this, so let's just copy this. Good enough. I'll have to remember the denominator, that's all. Okay, so this is equal to x squared plus y squared squared if we are not at the origin, and it's 0. So this is the partial of f with respect to y is equal to this. If we're at the origin. Okay. Good. Let's look at the, so from here we can actually just show that the mixed partials are not equal. So let's show that, because that'll be relatively easy from here. So let's look at the mixed partial not being equal. Okay. So mixed partials at the origin are unequal. So I'm only showing it at the origin, of course. So I'm going to show that at the origin, something weird is going to happen. So take the partial of f with respect to y and then x at the origin. So this is the limit. So we're taking the partial with respect to y of the partial with respect to x, of f with respect to x. So that k goes to 0. Of partial of f with respect to x at 0, 0 plus k minus the partial of f with respect to x at the origin divided by k. Okay, so this is equal to limit as k goes to 0. So let's look at the partial of f with respect to x. Okay, so that's this guy. Let me copy this so I know what I'm dealing with. This is partial with respect to x, yes. Okay, so let's plug in 0 for x, k for y. So 0 to the 4th k plus 4, 0 squared, k cubed minus k to the 5 divided by 0 squared plus 0 squared plus k squared minus the partial at 0 was just 0 divided by k. So this is equal to limit as k approaches 0. 0 plus 0 minus k to the 5th. 0 plus k squared is k squared is k to the 4th. Negative k to the 5th divided by negative k to the 5th divided by k to the 4th is a negative k. Minus 0 is negative k over k. So this is the limit as k approaches 0 of negative 1. And so this will just equal negative 1. Okay. And let's look at the other. So I'll have to do partial the other way. Negative 1. Now let's do the mixed partial, but in the other direction. So the other mixed partial. And so the derivative with respect to x of the derivative of f with respect to y. And so it's just a limit as h approaches 0 of the partial derivative of f with respect to y at 0 plus h minus the partial of f with respect to y at 0, 0, all divided by h. Oh, and I guess I should say that if I get kicked out like that, the time that the class ends is still the same. So even if I get kicked out, that just means the class doesn't meet as long because I got kicked out for those amount of time that the internet went out. Okay, so now let's plug in h0 to here. And so for x, we'll replace x by h, y by 0, replace x. So this is going to be divided by h squared plus 0 squared squared minus f of the partial of f with respect to y at the origin is still 0, all divided by h. Okay. And so this is equal to limit as h approaches 0 of h to the 5th minus 0 divided by h to the 4th is just h, minus 0 is just h, divided by h is 1. And so this is just a limit as h approaches 0 of 1, which will equal positive 1. So therefore, we have, I don't remember which way this was, xy is 1, yet the partial the other way was negative 1. And so the partials are not equal. So these two mixed partials are not equal to each other. Okay, good. Now, so I showed the mixed partials are not equal. This is kind of a long problem. Now I have to show that this is continuously differentiable. Okay. Well, it is differentiable because it's continuous at the origin. So f is differentiable. At the origin. Since F is continuous. And so is continuous at the origin. And while we can show that F is continuous at the origin by just looking at a limit. And so let's just see if the limit, I'll have to go up. I'm pretty sure I remember what the function is, but it's been such a long time since since the start of the problem. I better copy it to be sure I have the right function. Okay, so let's do that. Okay, so let's show that this is continuous at the origin. So I want to show that the limit that this limit here, I want to show that this limit is equal to this, okay? So first off, let's do polar coordinates. And so replace x by r cosine theta, y by r sine theta, r cosine theta, r sine theta quantity cubed over, of course, this will just be r squared, r cosine theta squared plus r sine theta squared. Okay, so this is equal to limit as r approaches 0. This will be an r to the 4 cosine cube sine theta minus sine theta, sine cubed theta. Cosine squared plus sine squared is 1, so this is just r squared. And so this just becomes r squared. It's the limit as r approaches 0 of r squared times cosine cubed. Where's the theta? Where is the theta? Oh, okay. Sine theta. He may have raised his hand too. Let's see. Oh. I mean the limit. To find the mixed partials, you always have to take the derivative to 0. No. And so if I understand what you're saying, so let's just see if I understand what you're saying. Okay, so the only reason that I'm doing this at the origin is because this function, because I ask, find the the partial at the origin. Show that the mixed partials are not equal at the origin. So that's the only reason I'm doing this at the origin. And due to the fact that I made this, this function was defined so that it's nice everywhere except at the origin. So it was defined as some, nice sort of rational function, which we know is continuous and differentiable everywhere, except when you divide by 0, and where you divide by 0 was at the origin. Did that answer your question? Is that what you're asking? Because I'm not sure if that was your question or not. Okay. Yeah, got it. Okay, okay. Okay, so let's factor out. So this is just r squared cosine cubed theta sine theta minus cosine theta sine cubed theta. Now, cosine cubed theta times sine theta minus cosine theta sine cubed theta, this is bounded. And so this is, this here is bounded probably by 2 or something. So this is probably somewhere between -2 and 3. It's a bounded, it's a small quantity, okay? And so I have something going to 0 times something bounded. I know that that goes to 0. So I know this limit here is 0. And so this implies that this limit f of xy is 0. And so since f of 0, 0 is 0, then I know that f is continuous at the origin. But actually, okay, so I know f is continuous at the origin. Now, let's see if this is differentiable at the origin. It'll be differentiable at the origin if I look at the mixed partials. So if it is differentiable at the origin, then the matrix representation for the derivative, the differential, will involve the partial derivatives. And so let's look at these partial derivatives, which we have calculated. And so now I'll look at these partials and see if these are continuous at the origin. That's x. They will do it this, they'll go exactly the same way. Okay, so I'll show that the first partials are continuous. The function is continuous, then the first partials are continuous. Then the function will be continuously differentiable at the origin. And so I just need to show that these mixed partials are continuous at the origin. So let me do that. So let's show that the limit as we approach the origin of the partial of f with respect to x, that this is equal to partial of f with respect to x at the origin. Okay, so let's do that. So again, let's let me get a little bit more room here. I know I need more room. And let me cheat. Let me put down the partial here so I know what it is. Okay, good. So now I can see it. Okay, so let's do the same sort of trick with polar coordinates. So let's do polar coordinates yet again. So let's do the limit as r approaches 0. Basically, if you have a good trick, you should try to use it in as many situations as you can. And if it works, then you're happy. If it doesn't work, you try a different trick. And so in my bag of tricks, I'm just using polar coordinates to try to simplify determining these limits. And so you may notice that a lot of times the techniques that we keep using over and over and over again are always very similar because it's a small bag of tricks that we have to choose from. Okay, so we'll do the limit as r approaches 0 of, so this is actually the first partial. So oops. So this here is the first partial. And so this will be r cosine theta to the 4th times r sine theta plus 4 r cosine theta squared r sine theta cubed minus r sine theta to the 5th over r squared cosine squared theta plus r squared sine squared theta squared. So this is equal to, actually before I erase it, let me just check once more to see that this is correct. 4, 1, 2, 5, and then squared squared. Okay, so this looks correct. Okay, so this is equal to the limit as r approaches 0 of, this will be an r to the 5th. What remains is cosine to the 4th theta sine theta plus 4. This again is to the 5th, so that's cosine squared theta that's r cubed, so that's sine cubed theta minus sine to the 5th theta over, well, cosine, well, I can factor out an r squared. Cosine squared plus sine squared is 1, squared, which is 1. So this is r to the 4th. And so I can cancel 4 of these. And I'll just get the limit as r approaches 0 of r cosine to the 4 theta sine theta 4 cosine squared theta, sine cubed theta, minus sine to the fifth theta. Now, this term here in the parentheses, again, this is bounded. It's probably somewhere between -6 and +. Certainly it's somewhere between -6 and +6. I'm not exactly sure how big it is, but, and so it's some bounded term times something going to 0, which will go to 0. Again, you could use the squeeze theorem. This is in between -6r and +6r. So as r goes to 0, the quantity in the middle goes to 0. So this is 0. And the partial of f respect to x at the origin, we said that this was 0. So therefore, well, I should also say that this implies here that the limit as we approach 0 of this partial is equal to 0. And since okay, that's good. Since, let's move this up. And since the partial of f respect to x at the origin is 0, then these are 0. These are equal to each other. So therefore, the partial of f respect to x is continuous at the origin. Okay. Next, I want to show that f of x, y, is continuously differentiable at the origin, yet that the mixed partials are unequal at the origin for the following function. F of xy equals the quantity xy times the quantity x squared minus y squared quantity, all divided by the quantity x squared plus y squared. If x squared plus y squared is not equal to 0, and it's equal to 0 if x squared plus y squared equals 0. So first thing to do is just to determine the partials. We determine the partial of f respect to x when x squared plus y squared is not 0 by just using the quotient rule. So it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. I then simplified that, just multiplying each of these together, combining like terms. Then I use the limit definition of the partial derivative to determine the partial derivative of f with respect to x at the origin. And well, I use a function at the origin. It was 0, and at any other point not being the origin, it had the form x, well, I multiply the xy inside the parentheses. X cubed y minus xy cubed over x squared plus y squared. I plugged in for x, h, for y 0. Well, this whole thing is, the numerator is going to be 0 divided by h squared is 0, minus 0 is 0 over h, which is 0. The limit is h goes to 0 of 0 is 0. And so I got the fact that the partial of f with respect to x is equal to this quantity. I did also the partial with respect to y, doing the same thing. If x squared plus y squared is not 0, then I use the definition above. It's just a partial derivative respect to y of a rational function. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Multiply these quantities together. Combine like terms. Use the limit definition at the origin. Both of these terms were zero, just like above. And so limit as k goes to 0 of 0 was 0. And so I got that the partial of f respect to y had this representation. With that, I could use the limit definition of the derivative to determine the second partials. So to determine these mixed partials, I just plugged in 0k above. Well, not this one. This was 0k above to get, and then 0, 0. To get that, well, this was equal to over k to the fourth, which is a negative k, minus 0, which is negative k, all divided by k, which gives you a negative 1. The limit is k goes to 0 of negative 1. And you do the same thing for the other mixed partial. It's just a limit as h goes to 0, where the x varies, and we fix the y coordinate at the origin. And so plugging in to the above formula, we got h to the fifth over h to the fourth, which is h minus 0, which is h divided by h, which is 1. Limit h goes to 0, 1 was 1. Therefore, the mixed partials were not equal at the origin. So the last thing we wanted to show, so now we'll go a little bit slower here, is that f was differentiable at the origin. Well, it turns out that f will be differentiable at the origin if both partials exist at the origin. They do. And, well, the mixed partials are continuous. Let me show that this function f is in C1, so that both of the partials exist and are continuous at the origin, and the function exists and is continuous at the origin. It's sort of overkill to show that the function is continuous at the origin, but I'll show this anyway. So you could just say the fact, well, if both partials exist and are continuous at the origin, then the function is continuously differentiable at the origin. But I'll show, in addition, that it's continuous at the origin, so that my functions are in C1. Okay, so I want to show that the limit as xy goes to the origin of f of xy is just f at 0, 0. So let's use polar coordinates. And so I'll replace x by x cosine, x by r cosine, y by r sine, r go to 0. And so I get r to the fourth, r to the fourth. So I can factor out r to the fourth. This is going to be r squared cosine squared plus r squared sine squared. So this is just r squared. So 2 of the r's cancel. So I get the limit as r goes to 0 of r squared times this quantity. This quantity here is bounded. It's bounded by 2, bounded between plus and minus 2 at least. And so I have something bounded times something going to 0. So therefore, by the squeeze theorem, this goes to 0. Since f at the origin is 0, And I've shown that the limit as xy goes to the origin, f approaches 0, then I've shown that f is continuous at the origin. And I believe actually this is where we ended last time. So now I want to show that each of the first partials are continuous at the origin. So I want to see if, as I approach the origin of the partial of f with respect to x, do I get the value of the partial derivative of f with respect to x at the origin? So let's use the same trick that we had from above. I will replace x by r cosine, y by r sine. So x to the fourth y becomes r cosine theta to the fourth times r sine theta, plus 4 x squared y cubed. So that becomes r cosine squared r sine cubed minus y to the fifth. So r sine to the fifth. Notice that these are all r to the fifth terms, so I can factor out r to the fifth. I have here an r squared in common. Sine squared plus cosine squared is 1. You square that, so this becomes r to the fourth. So 4 of the r's cancel. And what remains is cosine to the fourth sine plus 4 cosine squared sine cubed minus sine to the fifth. Well, I have here an r, which is going to 0. I have this, which is bounded by between plus and minus 6. And so, since this is bounded between positive 6, I have that by the squeeze theorem. Negative 6r goes to 0. Plus 6r goes to 0. This term, which is squeezed in the middle, also goes to 0. We know that the first partial, so therefore the limit as xy goes to the origin of the partial of f with respect to x at xy is 0. And the partial of f with respect to x at the origin is 0. Therefore, these are equal. Since these are equal, I have that f, the partial of f with respect to x at the origin is continuous, or that the partial derivative of f with respect to x is continuous at the origin. Similarly, the partial of f with respect to y at the origin is continuous. So you want to show that the limit as xy goes to the origin of the partial of f with respect to y is equal to the partial of f with respect to y at the origin. So do the same polar coordinate substitution. So the limit as r goes to 0 of replace x by r cosine, y by r sine theta. And so I have here each of these. So this is r to the fifth. R cubed times r squared is r to the fifth. R times r to the fourth is r to the fifth. So everything in the numerator has the factor of r to the fifth. Cosine squared plus sine squared is 1. And so I have r squared is r to the fourth. I can factor out cosine to the fifth, cosine to the third, sine squared, and, well, it's minus 4, of course, so those, minus cosine, sine to the fourth. And so, again, I have the limit as r goes to 0 of, well, r, so this goes to 0, and this thing, which depends on theta, this is bounded by between plus and minus 6. So if I look here, there you can determine a bound on this. And so again, just like above, I have that negative 6r and positive 6r go to 0. So by the sandwich theorem, this term here also goes, this limit here also goes to 0. Therefore, we have shown that the limit as xy goes to the origin of the partial of f with respect to y of xy is 0. And since the partial of f with respect to y at the origin is 0, then I've shown that these limits are the same. Therefore, the partial of f with respect to y is continuous at the origin. Therefore, f is C1 at the origin. But we know that if a function is C1 at the origin, then it is continuously differentiable at the origin. So I've shown that this function is continuously differentiable at the origin. Okay, so that finishes off. So even though the mixed partials in this case were not equal, the function was continuously differentiable at the origin. So even if the function is continuously differentiable at the origin, that does not imply that the mixed partials are equal at the origin. Okay, so now let's do the next example. Any questions on this example? I sort of finished it off kind of quickly. Okay, so if there are questions at the end, I'll also answer them. Okay, so let's do the following example. One second. Let me see what that is. Actually, let me move this down one more so it looks a little nicer. Yes. No. Oh, so something completely different. Exam 2 is only on chapter 14. So exam 2 is on chapter 14. Exam 2 is up. If you go to Canvas, exam 2 is already available for you to download and to start working on. It is due 1 week from today, unless I see that we haven't gone far enough. I want to be sure that I finished all of chapter 14, and you've had like at least a few days to work on it. So I believe I should be done with chapter 14 this week, and then you'll have, well, you have this whole week to work on it. Okay. Let me do the next example. So let f of x, y equal x squared y over x to the 4th plus y squared. If xy is not the origin, and it's 0 if xy is equal to the origin. So I want to show that all directional derivatives of f exist at the origin. I then want to show that even though all the, so that means that all partial derivatives exist. Not only do all partial derivatives exist at the origin, all derivatives exist. So no matter what, so like the partial of f with respect to x is a partial derivative in the direction of the standard basis I. The partial derivative of f with respect to y is a partial derivative in the direction of j. And so these are special, the partial derivatives are sort of special directional derivatives. They're just in the direction of your particular axes. So not only will all partial derivatives exist, they'll exist in every direction. So the directional derivatives will exist in every direction at the origin. But this function is not differentiable at the origin. So just the fact that things exist will not tell you that it's differentiable. So in the above, in the previous, I was able to say it was differentiable at the origin because not only did the partial derivatives exist, but they were continuous. So the fact that they were continuous made the implied that the function was continuously differentiable. Okay, so let's show that we really can't relax that restriction because we have counterexamples. This one. Okay, so first let's show that all directional derivatives exist at the origin. So before I do that, I have to tell you the definition of directional derivative. Please note that in two sections where we have a whole bunch of problem. That whole section involves directional derivatives. So I'm going to do some directional derivatives, but in the near future, maybe today or tomorrow, we'll be able to do more stuff on directional derivatives. There's a whole section on it. So let's determine the directional derivatives of x, y at the origin. So first, I guess I want a direction. So let u be a unit vector. Since it's a unit vector, I can just say it's of the form cosine theta, sine theta, for some fixed theta. So I'm going to fix theta here and then say, okay, I'm in that direction. This is a unit vector. So it's a unit vector. So the length of it is 1, and it's two-dimensional. We're in 2 dimensions. So the definition of the directional derivative of, and we denoted the directional derivative as uppercase D with a the vector, the direction that we're in. So this unit vector, F, and then it'll be at some vector. Actually, I'll write it this way because that's how we defined it. Not that it really matters. And so the directional derivative with respect to some vector, unit vector, of in the direction of the unit vector u, f at some point a, vector a, is the limit as t goes to 0 of f of the vector a, the origin in this case, plus t times the unit vector, which in this case is cosine sine, minus f at a. Okay, so t times a vector, cosine sine is just the vector t cosine comma t sine. You add that to the origin, you just get the vector t cosine comma t sine. Evaluate at the vector is just this first term becomes f evaluated at t cosine theta comma t sine theta, and similarly f evaluated at the vector 0 0 is just f evaluated at the point 0 0. So let's take the limit here as t goes to 0. Well, by definition, that's again t is approaching 0, so therefore t is not 0. And so these are not both simultaneously 0. So I can just plug in for sine theta for y, t sine theta. And so I get t cosine theta squared, t sine theta divided by t cosine theta to the 4th plus t sine theta squared minus f at the origin, which is 0, divided by t. Dividing by t is the same as multiplying by its reciprocal, 1 over t. This is a t squared times t is t cubed, cosine squared sine. I have here a t squared sine squared, a t to the fourth cosine to the fourth. So I can factor out t squared. What remains is t squared cosine to the fourth plus sine squared. The t square times t becomes t cubed, which cancels with the t cubed in the numerator. So I just get a cosine squared sine times t squared cosine to the fourth sine squared. As t goes to 0, this goes to 0 because theta is fixed. Since theta is fixed, I don't have to do any bounds, nothing of that sort. Theta is just a number. Therefore, a number times 0. And so I get cosine squared sine divided by sine squared. One of the signs cancel. Oops, what happened to that? One of the signs cancel. So I just get cosine squared divided by sine. So cosine squared times secant of theta. Well, that's just a number. And so the directional derivative is equal to some number, nice thing that's defined. And so all these directional derivatives exist. They're all equal to something. Okay. Yeah, I'm sorry. Just thinking for 1 second, because if theta was 0, they all exist except for multiples of pi, because then your sign is going to be 0. I guess I should say that all directional derivatives exist at the origin, except for those, except where theta is a multiple of pi. So that means except for an angle of 0 or pi. So except in the x direction. So that's the only one. So well, except all directional derivatives exist except for the one in the direction of x. If you took the partial of that with respect to x. Okay, so that's the only one that doesn't exist. Okay, so let's show that f is not differentiable at the origin. Well, remember, if a function is differentiable at the origin, then it's continuous at the origin. So that means that if a function is not continuous, then it cannot be differentiable. It's doing the contrapositive. So putting the arrow in the opposite direction. And so let's just show that the function is not continuous at the origin. So let's go along the path y equal kx squared. So I'm going to replace x by x, y, and so I have here an x squared y divided by x to the fourth plus y squared. So this, and I'm going to let x go to the 0. So therefore, both x and y cannot both be simultaneously 0, no matter what. And so x is not 0. So I have here k times x to the fourth in the numerator. I have here an x to the fourth, x squared is x to the fourth. I can factor that out. What remains is 1. So therefore, this is just a limit as x goes to 0 of k over 1 plus k squared. Well, it's a constant. Therefore, the limit is just k over 1 plus k squared. But that's going to have differing values depending on what k is. You know, if k is a -1, it's -0.5. If k is 1, it's +0.5. So depending on what k is, you're going to get different. This limit does not exist. So limit as x, y goes to the origin of f of x, y, that doesn't exist. Therefore, the function cannot be continuous at the origin. If a function is not continuous at the origin, then the function is not differentiable at the origin. So now, subtleties. Okay, so let me do and let's see if you can understand what's wrong. So what I'm going to do is I'm going to redo this limit here. The limit as xy goes to the origin of f of xy. And I'm not going to go along this path. I'm going to do it a different way. So I'm going to try to show that I'm going to try to determine the limit of this using polar coordinate change. So let's do this. So for the above function, let's do the limit as r goes to 0 of f of r cosine theta, comma r sine theta. So I'm going to replace x by r cosine theta. So that's a r cosine theta squared, r cosine theta to the fourth. And I'm going to replace y by r sine theta. So that's a r sine theta squared. So this is r squared times r. So that gives me an r cubed. Cosine squared sine. This is r to the fourth, r squared. So I can factor out r squared. What remains is r squared, cosine to the fourth, plus sine squared. The r cubed and r squared cancel. You just get an r. And so now let's take the limit. And this is going to be very similar to what I did like 2 minutes ago. And now you tell me what is wrong. So I have here r. And r goes to 0. I have here cosine r squared, cosine to the fourth, sine squared. And r is going to 0, so this guy here goes to 0. Just like what I did up here. And I said, well, this guy goes to 0, so you get this, okay? Okay, so now I got a cosine theta, the sine theta over sine squared. So that's just cosine squared theta over sine theta. And I have r going to 0. Therefore, this whole thing goes to 0. But that cannot be the answer. That is wrong. Why is it wrong? Because 2 seconds ago, I found out that the limit doesn't exist. If the limit doesn't exist, how can it equal 0? What am I doing wrong? So you would think we can do the following, but it is incorrect. So the question is why? Why can I not say that this goes to 0, and therefore something that's fixed and bounded, or something that's bounded, I gave the answer away, something that's bounded times something going to 0 goes to 0. Why have what I said, what is wrong with that logic? Anyone? Oh, good, I didn't say it. So can anyone think, what is wrong? What have I done wrong? Okay, not all at once. Okay, so I guess I'll have to tell you. Okay, so the problem is that in the previous thing, in the previous examples that I've given you, please note that when I did the limit, I had something bounded, sign something going to 0. And I was able to do that because no matter what I did the theta, it always was bounded and nothing bad happened. Here, unfortunately, what if R goes to 0 in some fixed fashion? So maybe it goes to 0 where, say, R is the same as sine of theta. So it goes to 0 in that fashion. In which case, then this will not go to 0. It'll go to something like cosine of theta over cosine squared plus 1 or whatever. So it'll go to cosine squared over cosine squared plus 1, but it's going to not go to 0. It's going to go to something fixed. Okay, so this will not be 0. And if you let it go as k sine theta, it's going to give you what I got from above, the k over 1 plus k squared. So the fact that I can't just say, oh, this guy is bounded, because there could be a way that I could go to 0 where this whole thing here does not go to 0. Okay, so you have to be a little bit more thoughtful when you do this limit. Okay, because it's not of the form where I've had it before. It's not where I could do something bounded times something going to 0. Okay, so be careful. So if you can find the limit legitimately, then this technique works. But this technique doesn't work, obviously, if you find the limit, but you do the limit illegitimately. So if you do the limit in an illegitimate fashion, it will not give you the correct answer, is all I can say. Okay. Okay, so let's do another example. Let f of xy equal x squared y squared over x to the fourth plus y to the fourth. If xy is not the origin, and it's 0 if xy is the origin. So I want to show that each of the partial derivatives exist, but the function is not continuous at the origin. Again, similar to the thing above, purely existence does not give, of the partials, does not give differentiability only if these partials existed and were continuous at the origin. Would that imply that the function is continuously differentiable at the origin? So only in the case where f is C1 will this imply the function being differentiable. Okay, at the origin. So let me use the limit definition of the partial derivative to find the partial of f with respect to x at the origin. So it's the limit as h goes to 0, f 0 plus h, comma 0, minus f 0, 0, all divided by h. So let's replace x by h, y by 0 in the above formula. So this will equal limit as h goes to 0, h squared, 0 squared divided by h to the 4th, 0 to the 4th, minus, well, f at the origin is 0 divided by h. 0 times h squared is 0 divided by h to the 4th is still 0, minus 0, still 0, divided by h is still 0. So limit as h goes to 0 of 0 is 0. Similarly, take the partial of f with respect to y at the origin. Limit k goes to 0. F of 0 comma k minus f of 0 comma 0, all divided by k. Replace x by 0, y by k. So I get the limit as k goes to 0. 0 squared, k squared divided by 0 to the 4th plus k to the 4th. 0 times k squared is 0 divided by k to the 4th is 0, the origin. 0 minus 0 is 0 divided by k is, oops, that's a horrible typo, is 0. The limit as k goes to 0 of 0 is 0. So therefore, both the partial of f with respect to x and the partial of f with respect to y, they both exist and are equal to 0 at the origin. So now I want to show that the limit as xy goes to the origin of f of xy does not exist. Okay, so let's just go along lines. So let's take the limit as x approaches 0 of f of x comma kx. So I'll take the limit as x goes to 0 of, I'll replace x by x, y by kx. So it's x squared, kx quantity squared, over x to the 4th plus kx to the quantity to the 4th. I have an x squared, so I can factor out x to the 4th, k squared. And I have an x to the 4th and x to the 4th here. So I can factor out x to the 4th. What remains is 1 plus k to the 4th. The x to the 4th cancel. So this is the limit as x approaches 0 of k squared over 1 plus k to the 4th. Well, that's a constant. So limit as x goes to 0 of a constant is just that constant. But again, depending on what k is, you know, let k equal 1, let k equal 2, you'll get two different answers. Therefore, the limit does not exist. And so this limit as xy goes to the origin of f of xy does not exist. Therefore, the function is not continuous at the origin. If a function is not continuous at the origin, then it is not differentiable at the origin. Any questions? So notice that this, you should see a pattern. So there should be a pattern that is emerging in all of these examples and how I've shown these examples. Yeah. Yes. So even if a function is not differentiable, so so this is the bizarreness of of multivariable calculus. It's because people unfortunately think that partial derivatives are derivatives, and they're not. Okay, so a function, even if a function is not differentiable, yes, the partial derivatives can still exist, and that's perfectly fine. Matter of fact, that this is what this is showing you. The partial derivatives exist, uh, yet the function is not differentiable. If the partial derivatives exist and are continuous, then the function is differentiable. Yes, these will be up. Oh, actually, these are uploaded. Uh, they will be uploaded to Canvas, but they're also, if you go into Tech Connect SSO and you look under recordings, they're all there. So all of the lecture notes are there. I will further put them into, I'll collect them so that they are done section by section, not only by way of classes. So if you want to go back and view the lectures of the classes, you can do that. I will then recollect them and put them in for each section. You can also find them that way, okay? Ooh, ooh, ooh. There's lots of files. So they're like 6 files. You'll see like there are lots of, if you click on, some of them are purely audio. Some of them are just the transcripts, the when you say the transcript of what I'm saying. So there'll be text to everything. So if you look there, and there's another one where it's a streaming, and corresponding to those, there's also the ones that are streaming. Click on the one that's an MPEG. That it looks like a little videotape. If you click on that one that has the picture, it has everything that you want. Okay. So yes, there are lots of files there. Basically, keep clicking onto the one you see, the one that works. It gives you the video. Okay. Again, there's a little icon next to it that looks like a videotape, a VCR, whatever it's called. One of those tape things. Okay, so let me do another example. So again, you should see a pattern that's emerging. One second. Let me get the chat up. Oh, the group work. I'll be telling you in the near future, I'll say, okay, today let's do a group work. And the group work will be I'll both say it during lecture and say it, I'll post it on Canvas. It'll be similar to, like, it almost has to be run like the way you do exams, where you'll click on something, you'll do it, and you can be, you can ask all your neighbors and everyone else, and then it'll be due in a few hours or something, and online, just like you would for the exam. Okay, so that's it. Okay. No, we've got to close it no matter what. Okay, so let's do the next example. I think this is the last example. And this one, I'll actually explicitly, I have to explicitly give you the derivative. Okay, so let f of xy equal x squared sine 1 over x plus y squared sine 1 over y if x times y is not equal to 0. So that means both x and y are not 0. Neither x nor y can be 0. Is equal to x squared sine 1 over x if x is not 0, but y is 0. It's equal to y sine 1 over y if x is 0, but sine is not 0. And it's equal to 0 if both x and y are 0. Now what I want to do is show that the partial derivative of f with respect to x and the partial derivative of f with respect to y are not continuous at the origin. Yet, f is differentiable at the origin. Okay? So, let's do that. So the partial derivatives will again exist, but they'll not be continuous at the origin. And so, my function is still differentiable at the origin. So let's find the partial of f with respect to x when x and y are both non-zero. So I'll use the product rule. The derivative, so it's an x squared sine of 1 over x. Derivative of x squared is 2x times the second, sine 1 over x, plus x squared times the derivative of sine 1 over x. Derivative of sine is cosine 1 over x times the derivative of what's inside. The derivative of 1 over x is a negative 1 over x squared. And so the x squares cancel. So therefore, I get 2x sine 1 over x minus cosine 1 over x. Let's do this at the origin. So let's take the limit as h approaches 0 of f of h comma 0 minus f of 0, 0 all divided by h. Well, let's plug in for x, h. So I just get, and notice that since y is 0, it's one of those special cases where if y is 0 and x is not 0, then the function was x squared sine 1 over x. So let's replace x by h. So it's h squared sine 1 over h minus f at the origin is 0, all divided by h. I'm taking the limit here. So this is just the limit as h goes to 0 of, well, one of the h's cancel. So it's an h sine 1 over h. But even though h goes to 0, in this acts very bizarrely, sine 1 over h, it's still bounded between plus and minus 1. And so, to take the limit as h goes to 0 of sine 1 over h times h, well, sine 1 over h is bounded between plus and minus 1. Therefore, by the squeeze theorem, h times sine 1 over h goes to 0 as h goes to 0. Next. Let's take the partial. Oh, so therefore the partial of f with respect to x is 2x sine 1 over x minus cosine 1 over x if x is not 0, and is 0 if x is 0. Let's take the partial of f with respect to y. Again, this is if x and y are not 0, then I'm just taking the partial of x squared sine 1 over x plus y squared sine 1 over y. Of course, the partial with respect to x, but with respect to y, it gives me 0 for that first term. So for the second term, partial with respect to y of, well, y squared gives me a 2y. I'll use the product rule. So it's the derivative of the first times the second. The derivative of y squared is 2y times sine 1 over y plus the first y squared times the derivative of the second. Derivative of sine is cosine 1 over y. Evaluated what's inside 1 over y times the derivative of what's inside. The derivative of 1 over y is negative 1 over y squared. So I'll just rewrite the 2y sine 1 over y Positive times negative is negative. The y squares cancel. So I get cosine 1 over y. And just like before, the partial of f respect to y at the origin is just the limit as k goes to 0 of f of 0k minus f of 0, 0, all divided by k. If x is 0 and y is not 0, then f of xy is just equal to y squared sine 1 over y. And so replacing y by k, I get k squared sine 1 over k. F at the origin is 0, so minus 0, all divided by k. And I take the limit here as k goes to 0. So this is a limit, k goes to 0, of one of the k's cancel. So k sine 1 over k. Again, sine 1 over k is bounded between plus and minus 1. And so this is bounded between minus k and plus k. Therefore, as k goes to 0, this whole thing goes to 0 by the sandwich theorem. I keep switching between calling it sandwich and squeeze theorem. It's whichever one you want to call it. Okay, so therefore, the partial of f with respect to y is 2y sine 1 over y minus cosine 1 over y if y is not 0, and it's 0 if y is 0. Okay, so okay. So now let's look to see if the partial of f with respect to x is continuous at the origin. So let's take the partial of f with respect to x at x0 and take the limit as x goes to 0. Okay, so let's do that. It's the same. Actually, it looks the same as this, except instead of having y's, there are x's here. This whole thing it looks the same. So let's take the limit as x goes to 0 of 2x sine 1 over x minus cosine 1 over x. Well, as x goes to 0, this first term here, cosine of 1 over x as x goes to 0, this keeps oscillating between plus and minus 1. So this limit doesn't exist. So a limit not existing plus a limit that does exist gives me some limit that does not exist. So cosine 1 over x does not exist as x goes to 0, but sine 2x times sine 1 over x does go to 0 because 2x sine 1 over x is bounded between, 2 sine 1 over x is bounded between plus and minus 2. And so this term here is bounded between plus and minus 2x. So as x goes to 0, the thing in the middle squeezes to go to 0 by the squeeze theorem. Okay, so since the limit doesn't exist, then it's not continuous. So the partial of x with respect to x is not continuous at the origin. Similarly, the limit as y goes to 0, the partial of f with respect to y at 0y is just, well, the limit as y goes to 0 of 2y sine 1 over y minus cosine 1 over y. This first term is bounded between 2y and positive 2y. And so as y goes to 0, this first term goes to 0. But cosine 1 over y, os limit here doesn't exist. So something that exists plus something that doesn't exist does not exist. So limit doesn't exist. Therefore, the partial of f with respect to y is not continuous at the origin. But the function is continuous, is differentiable at the origin. It's also continuous at the origin, but We want to show it's differentiable at the origin. So let's do a little bit of algebra. So we'll do algebra, arithmetic, to sort of show that this is differentiable. So instead of using calculus, we use some arithmetic, some algebra. So f is differentiable at some point, some vector a, if the change in f at a, so for functions to exist at a certain point, for function to exist at a certain point, no, that is not correct. I hope I didn't say that. So a function, certainly a function can exist without partials existing. Just think of, you could have a function that looks like this, like this, and then does something else. Certainly there, the function doesn't have any partial derivatives or anything. It's not even, continuous or anything else. But for a function to be continuous at a point, the limit must exist and equal to the value of the function at that point. Therefore, for a partial derivative to be continuous, the partial derivative must exist, and the limit as the point approaches that of the partial derivative the limit must exist and equal to the value of that partial derivative at that point. Okay, it's just that we're showing that this is continuous. So it's the same limit definition of continuity. As you approach your function, you want that function to have the value, the same value as the function at that point. Okay. So for f to be differentiable at some point a, we have to have the change in f at a evaluated at some small delta is equal to the derivative, the differential of f at a as a function of that little change plus little o of that little change. And so at delta of f at the origin evaluated at this little change vector h comma k is f of the vector, the origin, plus this little change. So it's a plus delta x. The change in y is f of a plus delta x minus f of a. And so it's f of the origin plus the little change minus f at the origin. So the origin plus hk is just hk. So this is f of hk minus f at the origin. Well, f at the origin is 0. So it's just f of hk. So x squared sine 1 over x plus y squared sine 1 over y becomes, well, we replace x by h, k by y by k. It's h squared sine 1 over h plus k squared sine 1 over k. Notice this is little o of h and little o of k. So these terms here are the error terms, meaning for h and k not being 0, the derivative, the differential is 0. Now let's do it. Where h is not 0. So delta f at the origin evaluated at the vector h0. So again, the change in y is f of the origin plus hk minus f at the origin. The origin plus h0 is just h0. So it's f of h0 minus f of 0, 0. Well, again, f at the origin is 0. F of x0, if x is not 0, is x squared sine 1 over x. So replacing x by h, you get h squared sine 1 over h. This, again, is an error term. This term goes to 0 faster than h. So this is a delta x squared term. It goes to 0 faster. And so it's just an error. Lastly, let's assume k is not 0. And so delta f at the origin, evaluated at 0, the vector 0k, is just f at the origin plus 0k minus f at the origin. So again, the origin plus 0k is just 0k. So this is f at 0k minus f of 0, 0. So again, f of 0, 0 is 0. So f of 0k, well, if k is not 0, then f not 0 is y squared sine 1 over y. Therefore, f of 0k, where k is not 0, is k squared sine 1 over k. This, again, goes to 0 faster than k. So this is, again, going to 0 faster than delta x if you're doing this in calculus 1. And so that's an error term. That's just, we disregard those things going to 0 faster than delta x. We're only worried about things going to 0 in terms of delta, the same order as delta x. So I state the following, that's obvious, that, and we'll show this, that the linear functional, the differential, df at the origin is just the 0 functional. It's always, no matter what you evaluate, you always get 0, how you evaluate it, you always get out the value 0. And so I want to show that delta f at the origin evaluated hk is just little o of hk. So I want to show that the following is little o of hk. And I'm just collecting all those answers I got above. So if hk is not, the delta f was h squared sine 1 over h plus k squared sine 1 over k. If h were not 0, it's h squared sine 1 over h. If k were not 0, it's k squared sine 1 over k. So back when we started this chapter, I gave the fact that I proved a lemma, that the absolute value of a was less than or equal to square root of a squared plus b squared. And I use that a lot of times, so I'm going to use that here. So now let's look at the limit as hk goes to 0 of h squared sine 1 over h plus k squared sine 1 over k divided by the square root of h squared plus k squared. By definition, if this goes to 0, then that means that this term is little o of hk. So to show that this is little o of hk, I just want to take each of these terms, divide by radical h squared plus k squared. That I want to show that this goes to 0 as h and k go to 0. So let me rewrite this slightly as h squared over, oh no, it's h as h o squared plus k squared, 8 and then times h sine 1 over h plus k over radical h squared plus k squared times k sine 1 over k. Well, I have that by this, h over h radical h squared plus k squared is bounded between plus and minus 1. Sine 1 over h is bounded between plus and minus 1. Therefore, as h goes to 0, this term goes to 0. It's bounded between plus and minus 1. This is also bounded between plus and minus 1. This is bounded between, the whole thing is bounded between plus and minus h and k in absolute values. So maybe I'll just say it with one of them. So this is bounded between plus and minus h. So this goes to 0 as h goes to 0. This is bounded between plus and minus k, and this goes to 0 as k goes to 0. So this whole thing goes to 0 as h and k go to 0 of the squeeze theorem. And so this whole thing goes to 0. Therefore, this first term above is little o. Now let's show that the second one, let's show that this next one is little o. It's the same thing. And so, well, oh, I didn't even state it. So let's show that this is little o. Again, divide by radical h squared plus k squared. Write the h squared, split it off this way. This is bounded between plus and minus 1. This is bounded between plus and minus 1. Therefore, this whole thing goes off to 0 by the squeeze theorem. Do the same thing for the next one. Well, this is bounded between plus and minus 1. This is bounded between plus and minus 1. Therefore, as k goes to 0, this goes to 0. So I've shown that this, which is your delta f, is little o. And so the differential is 0. It exists and is equal to 0. Therefore, f is differentiable at the origin. And we're done. Oh, and that's just an accidental page that was attached at the end. So any questions about that? So I've actually explicitly shown that the function is differentiable at the origin, and not only at the origin.